Right, so let's start putting some numbers around this concept. In order to measure temperature, we need to find some property of a material that changes in a nice reproducible way as a function of temperature. As we will soon see, as materials heat up, they expand. Both solids and fluids expand when heating, and we'll see this in the next lecture. The fact that a liquid expands when it gets hotter has been exploited to make a device that we use every day to measure temperature. This, of course, is a simple thermometer, the simple glass thermometer. Let's draw a schematic. In a normal glass thermometer, we have a lot of fluid in a reservoir in the bulb at the bottom and a very thin evacuated tube at the top. What's clever about this setup is that a small percentage change in the volume can then be seen by the naked eye. So if we draw some markers on the glass, we can start to define a scale. But an arbitrary scale isn't good enough. We need a scale that everyone agrees on. The points that were agreed upon concern the properties of a very common material on Earth, water. And we also need some units. So I went to the Swedish astronomer Andreas Celsius, who invented, obviously, the Celsius scale back in 1742. The Celsius scale has 0 at melting point of ice and 100 at the boiling point of water. But we have another temperature scale we also use in science, and that is the scale of Kelvin. This was postulated by the Irish physicist William Thomson, who went on to become Lord Kelvin. In 1948, Lord Kelvin wrote a paper that defined the lower limit for cold temperatures at minus 273 degrees Celsius. His temperature scale starts at 0 Kelvin and so is shifted by 273. There is still 100 divisions between the melting point of ice and the boiling point of water in the Kelvin scale. Note that the convention is to write Celsius as degrees Celsius, but Kelvin is just K, Kelvin, no degrees. So translating between the scales is easy. The temperature in Celsius equals the temperature in Kelvin minus 273.15. And of course the inverse, the temperature in Kelvin equals the temperature in Celsius plus 273.15. It's easy to remember, Kelvin should always be the higher number. And most of the time we just use 273 and drop the 0.15. But let's think a little bit more about the lower limit defined by Lord Kelvin for a moment. In fact, the fact that there should be an absolute lower limit for temperature based on our everyday understanding of temperature is not at all obvious. In fact, it's quite anti-intuitive. It gets colder and colder, but we don't ever think about it being absolutely cold where it can't get any colder. In order to understand this, we have to think a little bit more deeply about temperature. But if we instead think about temperature as a measure of hot and cold, and it is proportional to the kinetic energy of each molecule in a material, we can start to better understand this fact. We need to recall two things: the model of the structure of matter that we presented earlier, and from mechanics, remember that kinetic energy is related to movement. So then we can start to see that once a molecule slows down, the body drops in temperature, and thus there is a natural end, i.e. when the molecule stops moving, then the temperature is at absolute 0. More about this later, but it should be said that the molecules cannot stop moving completely, so we can never really get to absolute 0.